questions about yesterday? Hopefully, yes. I mean, I packed a lot of information into a very small amount of time.
When people talk about supersymmetry,
yes,
they have this like n equals blah thing. Was the one that we saw yesterday n equals 1 or?
So in the standard notation, they were 1,0 or 1,1.
Okay.
So the notation typically means how many supercharges you have expressed as a multiple of a minimum number that you can have in the dimension. And in even dimension, not just even, module equal to 2 modulo 4, you can have supercharges of different chirality. And so you need to give 2 numbers. It's a bit of a funny notation. Any questions? Okay, so I would like to mention first an important aspect of this GSO projection I mentioned. So, as you remember, you start from a theory which has some fermions, spin 1/2 fermions, and then you throw away all operators that have half integral spin. In exchange, you get new local operators which induce monodromies for your fermions. Now, because of this transformation law that I wrote, there is something interesting that happens when you look at the state operator map. For the state operator map, you do a coordinate transformation that looks like this. So this Jacobian becomes something like e to the s over 2. And in particular, the Jacobian is anti-periodic as you go around your cylinder, or if you go around the origin in the plane. So as a consequence, if you look at behavior under the state operator map, operators around which the fermions are periodic map to states on the cylinder for which the fermions around which the fermions are antiperiodic, and vice versa. So if you have an operator we call O and SNS with a property that as you bring it around O, psi is periodic and psi bar is periodic, then this maps to a state with a property that the operator psi of S acting on this state satisfies an antiperiodicity condition. And the same for psi bar. So that means that on the cylinder, when you expand your psi modes, you find modes which are half integral. Mm-hmm.
Why isn't this always true from the left, since e to the 2 pi I is just 1?
What this really means is they take psi and analytically continue it around this path. And it comes back to itself. If I look, say, at a Ramon sect operator, as you remember, it lives at the end of a cut in the original theory of fermions. So around it, when psi crosses this path, it gets a minus sign. So one way you could write this, it's just a silly notation. It's nothing. Okay. You write the psi of 2 pi e to the 2 pi I z is minus psi of z, which maps the statement that psi of s plus 2 pi Ramon is psi of s Ramon, etc. So in the Neveu-Schwarz sector, both psi and psi bar have half integral modes. In the Neveu-Schwarz-Ramon sector, psi will have half integral modes, and psi bar will have integral modes. In the Ramon-Neveu-Schwarz, the opposite. And in the Ramon-Ramon, they will both have integral moding. Any question? So the theory has four collections of operators, of states. Riemann-Hilbert of the theory, Riemann's Hilbert space of the theory splits into 4 sectors. So to get the correct Hilbert space, you look at the Fock space of the fermions, built from the oscillators in these 4 sectors. And then you impose the GSO projection, meaning that you only keep the states which have an even fermion number, both on the left, both on the chiral and antichiral side. So it's convenient to define some fermion number operators. Which anti-commute psi, but commute psi bar. So the statement is that so we're going to keep only the states for which minus 1 to the f and minus 1 to the f bar are 1. Mm-hmm.
So we map this operator out this state?
Yes.
And the operators side, they are in both?
Oh, sorry. This is how the fermion number acts on the operators. You have to also decide how it acts on the states in a way which is compatible with the state operator map.
So we also map psi.
So, for example, the identity commutes with f, right? So the state 0, the vacuum state, will have minus 1 to the f equal to minus 1 to the f bar equal to 1. Now, we need to also have, so this minus 1 to the f is just measuring the conformal dimension, something like e to the I pi times the 2 I pi conformal dimension. Okay. If you want to be e to the 2 pi I plus 0, that's also a fine definition. as a delta. 0 is probably better. Anyway. This also has to anti-commute with the ghosts, beta and gamma. And with a little bit of work, which I don't want to do now, you can figure out how these act on the ground states for the ghost system. So there is some state G, which is the ground state for the ghosts and super ghosts in the Neveu-Schwarz sector. Up here. This is analogous to the ground state we had in the bosonic string, the one that was dual to the operator C. It's a little bit more complicated to write down the operator dual to this. I'm not going to do it because we're not going to compute superstring amplitudes. But the important point is that this state has -1 to the f equal to -1 to the f bar equal to -1. So this is a very important consequence. When I look at the Fock space, the GSO projected Fock space in the Neveu-Schwarz sector, well, first of all, before I project, what is the Fock space for the fermions? So I define for you the modes. Remember, we had these anti-commutation relations. Right? So the Fock space, so in the Neveu-Schwarz sector, because n runs on the half integers, there are no zero modes. There are only zero modes for the bosons. So the Neveu-Schwarz sector has some ground states labeled by momenta on the matter fields, and then some states for the ghosts. Let me just put the ground state here. And then there is a Fock space that you build by acting with oscillators, things like psi -1/2 p tensor g, psi bar -1/2 p tensor g, psi -1/2 psi bar -1/2 acting on p tensor g, etc. So this will be the Fock space before the GSO projector. Now I need to GSO project. This has eigenvalues both -1, so it goes away. This has eigenvalue 1 and -1. So this changes the eigenvalue of -1 to the f, but not the one of -1 to the f bar. So this also goes away. This goes away. Only this is kept. In general, you only keep things where an odd number of psis and an odd number of psi bars act on the ground state. Any questions about this? Mm-hmm.
Why are we? I actually don't understand why we're only keeping states with -1 to the f and -1 to the f bar equal 1.
So I'm doing this operation where I'm doing this topological manipulation. It takes the theory and gives me another theory. In this topological manipulation, I keep some operators which are closed under fusion, under multiplication. And the simplest way to do so is to find some symmetry and say, I only keep the operators which are even under that symmetry. Because the product of such operator remains even. Okay. Instead, if I was trying to keep the ones that are odd, when I multiply through odd ones, I get an even one. So that will not be good. So I identified in the theory of fermions two symmetries. Choose the two symmetries. -1 to the f and -1 to the f bar. These are symmetries to the theory of fermions and ghosts. And as long as the number of fermions is equal to 2 modulo 8, these are non-anomalous symmetries, and I can really project on operators that are invariant under those, and then add twisted sectors, so-called, or Ramon sectors in this case, to make up a new theory which is well defined. Anyway, maybe I should say something quickly about that I only mentioned in passing yesterday. What do I say that the theory is well defined? Let me give an example of something which could fail. Suppose I want to study the theory in a torus. I compute something like the torus partition function. And I've picked some list of operators that I want to keep. Then I can apply the set operator map that gives me a collection of states that I'm conjecturing my theory to have. I can define the torus partition function by cutting and writing as a trace on this Hilbert space of something, of a time evolution. But I could take the same torus. This way I compute an answer. And then I can try to interpret that answer as a sum over states on a circle, but on a B-cycle circle. And I might discover that it's not a trace on the same Hilbert space anymore. So that's inconsistent. My theory should give the same theory, should assign the same space of state on a circle, no matter if it's this circle or this circle. So I get a constraint on the list of operators I included in the theory. That the partition function I compute only depends on the torus itself and not on how I cut it. That's one example of the possible constraints. Often this constraint is, so this is definitely a necessary constraint, is often sufficient, as so happens. Okay.
I think the last point it meant for a state to be an SNS or RNS.
It just means that in terms of the original fermions, the psi's are either periodic or antiperiodic when they go around the operator.
But then what does it mean to say R, NS?
It means the psi is periodic and psi bar is not periodic.
Oh.
It's antiperiodic or vice versa.
Can you just write down the projection? Something projection?
This is the condition. I want to impose this condition.
But the name of the projection that you're saying?
GSO, sorry. This is called in the string theory textbook GSO projection. Okay. Goddard. I don't want to say the names because I will miscite them, and some of them might still be around. Yes?
You described, I think yesterday, the GSO projection as being we wanted like an even number of fermions.
That's right.
And also an even number of type psi bar. How do I see that that's the same as what you've written there for NSNS?
You mean this?
Like, how does that relate to what you said yesterday?
Well, as you see, this counts the number of fermions. This is the symmetry for which the fermion operator is odd. So the even operators are operators which have an even number of fermions.
So it commutes with.
But it's just the statement that I'm including now operators. I want to include operators which have all sorts of possible periodicity conditions for my fermions. Okay? I can only do this consistently if I keep only operators with, if I have true local operators in the theory, the correlation function must be single valued. Otherwise, there is no locality. So if I decide that I want to include these guys and these guys, then I need to drop any operator which is not local with them. If I have a generic operator here, this will go to -1 to the f, -1 to the f bar, times the operator, as you bring it around. The sign I put here is just -1 to the f, -1 to the f bar. Sorry, let me just step back. Okay, so I have an origin. I have my initial theory, the theory of fermions. This theory has a collection of operators. I can decompose it as a direct sum of depending on the action of -1 to the f and -1 to the f bar. So I have some z2 times z2 symmetry, which generates -1 to the f, -1 of the f bar, which acts on my operators. Okay? I define it like this on the elementary fields. I can extend the definition to the Hilbert space, or the state operator map, and so on and so forth. Now, I want to build a new theory which only keeps these guys. But it includes now new sectors. Actually, oops. So in a sense, if I relax the requirement of locality, I can have 16 different sectors. I can have operators which impose certain boundary conditions on the fermions and which are odd or even under these -1 to the f, -1 to the f bars. And I have this bigger collection of operators, and I'm trying to define well-defined theories by taking mutually local collections of operators. So this is one. This is the original theory of fermions. This is another such collection. These are actually not the only collections that I could write. There are some small variants. But the possible freedom can just be reabsorbed into the redefinition of what I mean with -1 to the f, -1 to the f bar acting on these other sectors. So I will ignore that. So we're looking for this theory, starting from this theory. Okay? Yes?
Can you repeat what these operators with plus mean?
So these indices denote the action of -1 to the f and -1 to the f bar. Right? I have a vector space acted upon by two operators with square to 1, and which commute with each other. So I can just decompose it into eigenspaces for those operators. Those are the 4 eigenspaces. I can also look at twisted sectors, where I include operators which live at the end of a cut. So ORNS describes as local operators around which a fermion will be periodic, antiperiodic, and so psi will be antiperiodic and psi is periodic. There is a space of such local operators. And again, it decomposes into 4 eigenspaces as soon as I decide how -1 to the f and -1 to the f bar act on this space. And so on and so forth. So in general,
But decomposing into eigenspaces. So are you talking about the like the eigenvalues of the states that correspond to these operators when you do that?
no, operators are acted upon by the symmetry. Now there is an identical map, an identical 4x4 matrix of Hilbert spaces which are related to these operators by the state operator map.
Okay.
So if you take any operator, any operator in this table, and some other operator in this table, you can ask what happens if you carry one around the other. You get an overall sign, right? Essentially, it's a combination of, I don't know, you check if this operator has an R and the other operator has a minus, I get a -1. And I collect all these -1s for all the sector, for both symmetries and for both set of both operators. I get an overall sign, and I want this sign to be 1, +1. So the two operators are local with each other. So, but the simplest choices I can do is either to pick this 4 or to pick this 4. To pick this 4 is a reasonable choice, because when I multiply them with each other, everything will be fine, because they're all carrying no charge under the choose. And they are local with each other, because essentially they have, morally speaking, an even number. All of these have an even number of psi's and an even number of psi bars. So they don't see the antiperiodicity.
The two theories you circled admit a bijection in their local operators?
No, they're different theories.
Okay.
So sometimes it can happen that there is a miracle for which there is a bijection. For example, in the Ising model, I have a single Z2 symmetry, right? I have operators, sort of standard operators, even and odd under the symmetry. I can introduce new operators which live at the end of a cut. And decompose them again in terms of their charge under this two symmetry. So this is Ising. This theory, it's another Ising by a miracle called Camevani duality. And this theory is the free fermion.
Sorry, what is the duality between the two?
Oh, they're just two Ising theories. So it just so happened that this collection of operators is identical to this collection of operators in the way they multiply with each other, their dimensions, and so on. This didn't have to be the case. In general, it's not the case. Even if you just take two copies of Ising and you look at the diagonal Z2 action, then this will not be true anymore. This will be a new theory. In the context of this superstring theory, and notice, right, as I was saying yesterday, these two are standard conformative theories, while this requires a spin structure. In the case of the word volume theory for superstrings, the theory of fermions requires a spin structure, so I don't quite like it. This theory does not require a spin structure, so I like it more. Okay. Notice if I can sort of reorganize, I can give different names to this, right? This is also the operators of the free fermion theory. Which are even and in the next sector. These are operators of the free fermion theory, which are still in the next sector, but they are odd. These are the operators in the free fermions, which are Ramond and even, and these are operators in the free field in the free fermion theory, which are Ramond and odd. And there is a bit of ambiguity in deciding which of the Ramond states are even and which are odd. So the free fermion theory is a sort of allows you to redefine the way minus 1 to the f acts on the Ramond sector. So you exchange all of these two. So you see that when you decide to go from free fermion to Ising, there is a bit of a choice of which of the two you call even and which you call odd. In this setup, you get the same answer no matter what you do. You get Ising or Ising. Now, in the superstring, so you start from your x plus psi bar plus ghosts, and there are two different choices of what to do with the Ramond, with the definition of minus 1 to the f on the Ramond sectors. And one of them will give you the word volume theory of something called the type 2A string. In the other will give you the word volume theory of something called the type 2B. So there will be two different ways to define what's even and what's odd in the Ramond sector, and this will give me two slightly different, well, two quite different string theories.
Why? It seems so. The original theory was restricted to an SNS in just the period the parities variant. Why was that? Why was it an SNS?
An SNS is just the name you give to the operators around which the fermions are periodic. Just the name.
R. Whatever.
No, because the product of two Ramond operators is a Navier-Schwarz operator. So if I have an operator here on which psi is antiperiodic, an operator here on which psi is antiperiodic, if I carry psi around both, it goes back to itself. It costs two cuts. So whatever collection of local operators you call a theory, it should be closed under product.
Okay. So why should I not include both R and NS from the beginning?
Well, you cannot do that and at the same time have an odd number of fermions. Because I cannot have in the same theory the fermion operator and a Ramond operator, because they're not local to each other. If you bring one around the other, you change the sign, so you cannot give a meaning to correlation functions without putting cuts. If you put cuts is a different matter, explicit cuts. It's like when you discuss magnetic monopoles and Tuft operators, magnetic monopoles and electromagnetism. Integrally quantized magnetic monopoles make sense as particles. There is no need of it with an actual Dirac strength. If you try to define a magnetic monopole which is not properly quantized, is not mutually local with the electron, it cannot be a particle. You cannot have a local operator which creates a magnetic monopole or anything like that. Because in the same theory, we also have an electron. It can live at the endpoint of a string. If you have an actual physical string which has a monodromy of the gauge field, at the end of the string you can have something we can call a fractionally quantized monopole. But the question?
You keep saying that, like, if we had a correlation function,
Yes.
that pick up a sign when it went around itself, and
Yes.
that would mean that we couldn't have a local theory.
It's not, a correlation function is a recipe to give me a number once you give me the position of local operators. That's the only I can. That answer better remain the same if I take an operator for a stroll and until it comes back to the original position.
Okay.
Because the correlation function is supposed to only depend on the position of these operators, not on the history of how I envision the correlation function. Now, you can keep track of the history if you stop thinking about two-dimensional theories. There's a whole beautiful way to think about this in terms of topological field theories in 3 dimensions, but is not the reason the direction I should go in here. There's also a notion of something called conformal blocks. So a theory where the correlation functions are not single-valued is sometimes called a relative theory. It does not have correlation functions. It has something that is called conformal blocks. This is a poorly chosen name because it's a notion which applies to theories which might not be conformal, but people found this notion in conformal field theories, and so they call it conformal blocks. And there is a lack of a good name, unless you're a mathematician, in which case you call it factorization homology. But that's not a terminology which is used in physics. Anyway, so you can have something that generalizes the notion of conformal blocks, which is only defined locally and has not single valued when you bring your operators around loops. And then from that point of view, a tentative theory is a theory for which you can define conformal blocks, and a true theory is a theory where you can find one choice of correlation function inside the space of conformal blocks, which is single valued.
So even the correlation functions would be well defined if we take a cover of this plane, like a square root cover.
Yes.
Okay.
But the problem is that suppose I have 2 operators which are not mutually local with each other. Do I put a cut for one of them or for the other? So when you say I put cuts, I go to the universal cover, you have sort of already made a choice of which operators are true operators and which operators are ends of cuts. Okay, so here I'm doing this. This is the simplest vector inside operators of an S and S sector, which are even under both -1 to the F and -1 to the F bar. This is the simplest representative in that Hilbert space. Okay? Now, in order to discuss the other sectors, there is an important subtlety, which is that we have fermion zero modes. So if I'm in the Ramon NS sector, I have psi0 mu. And psi0 mu, psi0 mu, nu, anticommute to eta mu nu. Because as I said, in the Ramon sector, the fermion has an integral mode. It's expanded in Fourier modes, which have integral momentum. Now, do you recognize this algebra? Which algebra is that? Clifford algebra, that's right. So my Hilbert space must be a representation of this Clifford algebra. So I'm going to build a Hilbert space out of things which carry 2 labels. There is a momentum label, and then I need some label on which this Clifford algebra acts. Let me call it A. Now, actually, so which Clifford algebra are we talking about? How many directions do we have? Let me anticipate the following fact. Superstring theory will be value invariant quantum mechanically if the number of dimensions is 10. So 10 replaces 26. Essentially, what's happening is that while the bosonic gauss contributes -26 to the central charge, the fermionic gauss contributes +11, so it gives you -15. Then each direction of space-time contributes a boson and a fermion. the boson has central charge 1, the fermion has central charge 1/2. So each direction of the space-time contributes 3/2, and so I need 10 of them to get a 15, which cancels the -15. So this is the Clifford algebra of that you would use to study spinors of SO 9,1. So there are two chiralities for the spinors. I need them both to have a representation of the Clifford algebra. So I'll denote the states this way. So I have an index A that runs over a basis and the opposite chirality, and index A dot that runs over a space of negative chirality. And then the zero modes will act as gamma matrices. So if they act on PA, for example, they'll give you something like this. Remember that gamma matrices switch the chirality. I'm going to get expressions like that. Right? And similarly for psi acting on A dot. Okay, so this is the way that my zero modes act on these ground states. The reason I split them in two is because -1 to the f acts in an opposite way on this and this, right? Psi is odd. That means that if these guys are even, this must be odd, and vice versa. So let me pick the convention that -1 to the f is 1. On these guys combined with the ghosts, with the Ramon sector of the ghosts, and -1 to the f is -1 for these guys combined with the ghost. Okay. So that means that when I look at, I try to do to describe the GSO projected, right, this is RNS, yes, RNS sector. I started these momentum modes with both chiralities. And then I remove one of them. And then I can add with modes, right? I can put psi -1 mu PA dot tensor G. I'll definitely keep this because this is overall -1 to the f equal to 0. I can do things like A -1 mu PA tensor G, because the boson zero mode, the boson modes don't have a number. And same here. I get some. Now, here I get to make a choice. This choice was immaterial, that -1 to that this guy was even and this guy odd. But it clearly makes a difference to when I compare with the NSR sector, where now I have the psi bar zero modes, which are sort of a completely different set of gamma matrices. Now I have my PA RNS NSR and my PA dot NSR. And it, the two chiralities, for the spinors are really different this time. It makes a difference to say, I want to keep both both collections of states with the same chirality, or I want to keep collections of states with opposite chirality. These are called type 2b and type 2a. So here you have a choice. You can, if you want to do type 2b, you keep this. You drop this, or vice versa. So you keep this guy if you want to do type 2b. You keep this guy if you want to do type 2a, etc. And finally, there are the Ramond-Ramond sectors. In the Ramond-Ramond sectors, you have two different collections of zero modes, one for psi, one for psi bars. So now your states will have to carry two different spin or indices in space-time. So depending if you're doing type 2a or type 2b, you might want to keep these two. Sorry. Yes. Well, no, sorry. I'm doing. You always throw away the ones which have an A dot on the first slot. So these ones always go away, but you get to choose which one do you keep, depending on the second spinor indices in type 2b and type 2a. Okay, so this is the Hilbert space of the worksheet theory for type 2a or type 2b. I ignore the ghosts. Of course, on all of these, you can also act with ghost oscillators. Let me ignore that. Now, to get the spectrum of the strings or the superstrings, I need to still impose the BRST closed condition, modulo BRST exact states. So I need to understand how the BRST quantization looks like. Now, I'll do it in the sort of same ad hoc way we did in the bosonic string, where I just sort of Gupta blur-like, where I just tell you which modes of the stress tensor of the matter fields has to annihilate the state, the physical states. So in the Neveu-Schwarz sector, your stress tensor has the usual expansion in terms of L modes, Virasoro modes. Now the supercurrent is an expansion in modes which is half integral. So my physical condition will be something like I'm annihilated by Ln for n positive, Ln bar, L bar n, and also G n and G bar n. There are no zero modes for G. The only thing I need to worry about is the zero mode for L. And in the bosonic string, we had something like L0 equal to 1. because there was a Casimir energy from the ghosts that was -1. Now the Casimir energy is -1/2. So the condition is that 0 minus 1/2 annihilate the physical state. So this goes pretty much as before. This guy is the ground state, pretty much, because all the states at the lower energy have been thrown away. So clearly all of these conditions are automatically satisfied. You only need to check this condition. Well, I'm lying a little bit because what we really check, let's just say that you need to impose these conditions. I mean, it's perfectly possible for G1/2 acting on, so G1/2 acting on this will map you here. So although this is the ground state after G projection, I still kind of need to check this, that is annihilated by G1/2 and G bar 1/2.
L is given in terms of the bosonic A.
Yes.
So don't.
And also the psi's. So it's the total stress tensor.
Okay. Did we?
I think I wrote it down briefly. So something like 1/2 dx squared plus psi or minus psi del psi. Anyway, pretty much what's going on is that, okay, it's there is no subtlety here. I just express myself poorly. Let me just say that when you do things with the ghosts included, the BRST charge is even under -1 to the F and -1 to the var. So the BRST symmetry, the BRST operator definitely maps the states we are keeping into states we are keeping, but with some ghosts on them. So your theory has things that look like these with a ghost with something like gamma -1/2. So the BRST operator might map these into that with an extra ghost insertion, which is in this space of space. When I write things in the intuitive way here, this all means that when I check these conditions, I should check them even when the right-hand side is outside of the operators I would, or the states I would keep with the GSO projection.
So just from the perspective of the GSO projection, the ghosts contribute to the fermion number?
Yes, the super ghosts, not the BNs. It's funny, the beta and gamma contribute, because this is not quite a fermion number, although I call it -1 to the F. It's more precisely a spin number. It measures the spin of the operator rather than the fermion number of the operator, the Grassmann nature of the operator. So in a unitary theory, there is a spin statistic theorem. So if an operator has a half-integral spin, it's a fermion. But the ghost theory is not unitary. So the BNCs are fermions but have integral spin. The beta and gammas are bosons of half-integral spin. Anyway, so to make a long story short, the G1/2 condition still applies here, requiring the G1/2 kills this. G1/2 looks roughly like P psi 1/2. So when you do this calculation for these particular states, you get an on-shell condition from that. And thanks to the fact that there is psi 1/2 minus 1/2 here, this on-shell condition is P squared equal to 0. So these are massless states. And then if you put a polarization, the G1/2 condition just tells you again that P dot at P mu epsilon mu nu is 0, and gauge symmetries are epsilon mu nu goes to epsilon mu nu plus P mu lambda nu plus lambda tilde mu nu. So these states behave just in the same way as the A-1, A-1 bar behave in the bosonic string. These are massless. They are massless graviton, dilaton, and B field. So the NS sector of the superstring gives us the same fields that we found in the bosonic string at 0 mass. But it has no tachyon. If this had been included in the Hilbert space, it would have given a tachyon in the string theory, but it's not included. Now, in the NSR or in the RNS sectors, things are more interesting. Because now there are 0 moles for G2. So when I write down my conditions, I have, and actually G0 squares to L0. It's kind of fun. So these are going to behave exactly like the Hamiltonian and the supercharge that we encountered when we're trying to define fermions in first quantized formalism. So the on-shell conditions will give you some things like L0 for the physical state equal to 0, L0 bar minus 1/2 for the physical state equal to 0, and then G0 acting on the physical states equals to 0. So essentially what's happening is that the ghost ground state in the RNS sector has no Casimir energy for L0, but it has a Casimir energy for L0 bar. And so this guy, so this guy cannot contribute because this guy has the same L0 as L0 bar. So this cannot be on shell. But this can contribute with P square equal to 0. And then there is some Dirac equation, P dot psi equal to 0. So it's a state that corresponds to a fermionic field in space-time, which satisfies the Dirac equation, and it carries a spinor index and a vector index. There's a spin 3/2 massless field. Spin 3/2 massless fields are called gravitinos. And there is a general theorem that if you have a massless gravitino, you have supersymmetry. Actually, a super diffeomorphism invariance. Same way as the graviton tells you that you have diffeomorphism invariance. So the type 2 string theories end up having target space supersymmetry, space-time supersymmetry, even if you didn't put it to start with, because they have a gravitino. And actually, they have 2 gravitinos. There's a gravitino coming from here, and there's a gravitino coming from here. So type 2A has 2 gravitinos of opposite chirality. Type 2B have 2 gravitinos of the same chirality. Now, as you remember, I told you there is some people that at some point wrote down all supergravities. It's a very constrained exercise. And so at some point, they were classifying supergravities in 10 dimensions, and they found that there was a nice supergravity which had 2 gravitinos of the same chirality, and they called it type 2B. A nice supergravity that has 2, I don't know actually if they called it type 2B already. Anyway, they gave it a name. And there is a nice supergravity in 10 dimensions which have gravitinos of opposite chirality. And so, because these supergravities are very rigid, these pretty much tell you almost immediately that the low energy theory of these superstrings must be those supergravities. Now we have minus a few minutes to discuss the Ramon-Ramon sector. The Ramon-Ramon sector is particularly fun because now I have both a G0 equal to 0 and a G0 bar equal to 0. equation on shell condition. And also L0 equal to 0 and L0 bar equal to 0. So these states survive and are massless. So there are extra fields. So there are graviton, dilaton B field, gravitinos, and these other massless fields called Ramon-Ramon fields. Now these fields look very bizarre at first sight. They carry two spinor indices, and they satisfy two Dirac equations. Have you ever encountered a field which naturally carries two spinor indices and satisfies two Dirac equations? Yes, it's called electromagnetism. So suppose you're trying to describe electromagnetism in a first order formalism, writing down equations of motion in terms of the field strength instead of the connection. So you can take your F mu nu and contract with the gamma matrices. So the product of two gamma matrices has two indices to the same chirality. We call this F alpha beta. And then there is F mu nu, gamma nu, alpha dot, beta dot. Call it F alpha dot, beta dot. Now what to say is that the field strength, if you look at it as representation of the Lorentz group, split into two. There is the self-dual part and the anti-self-dual part of the field strength. And one can be thought of as carrying two spinor indices, symmetrized actually, and the other two anti-symmetrized spinor indices. Let's just count. The field strength has 6 components. Each half has 3 components. A symmetric matrix, a symmetric 2x2 matrix has indeed 2 components. 3 components, sorry. Now you can try to write down the equations of motion. And Bianchi identity in terms of these components. And they look like Dirac equations with Dirac operators acting on these spinor indices. So these are just generalizations of abelian gauge fields. So the way you understand them is you say, okay, I write my polarization, say for this. I just recognize the fact that the product of two spinor indices can be written in terms of more conventional representations of SO 9,1, like vectors or matrices with certain numbers of vector indices. This is a fun exercise, which maybe we'll do tomorrow if you have time besides the question answers. And the answer is that you get forms. You get things like, so in type 2A, you get a 1 form, like a Rayleigh gauge field, a 3 form, a 5 form, and so on. In type 2B, you get a 2 form, 4 form, and so on. So these are the Ramond vector fields. There are a bunch of massless fields that sort of, people knew they had to be there because of supergravity. They appear as when you try to write down a supergravity. But here you find them like this. So somehow these are organized naturally in terms of the field strengths of these fields. So the connections. So these two linear equations are completely analogous to this kind of equations. They are Bianchi identities and equations of motions for some field strengths, except that the field strengths have more indices. Right, so in type 2B, there are field strengths that look like F, sorry, mu nu rho, F mu nu rho sigma tau, and F mu, actually, which is secretly the gradient of an axion. And in type 2a, you have F mu, sigma rho. So actually, there is really no so on. It turns out that the other ones are just dual to these ones. And here you really take only the self-dual part. Discussing this will take too long. But essentially, the point is that if you wrote all the forms of all possible number of indices, then you would get something corresponding to all these four. Throwing away this half imposes a self-duality condition, and then picking one of the two halves gives you forms with even or odd number of indices. All of this is just exercises with gamma matrices. It's a fun exercise. It takes maybe an hour. Definitely worth doing. Maybe more than an hour. It depends on how familiar you are with gamma matrices.
And where are the fields with spin 1/2?
There are no fields with spin 1/2. Well, massless fields with spin 1/2 in the target space.
Okay, you need to go to higher mass?
That's right, with massive spin fields with a variety of indices. If you were to introduce D-branes in the picture, the open strings would naturally have both gluons and gauginos, spin 1/2 fields, which are partners of the gauge fields.
But for example, to obtain something like a Dirac field, what would you need to do, or where is it?
Again, this is all about 10 dimensions. Now, if you were to replace some of these 10 dimensions with some other CFT, you will get a variety of different spectra which can have spin 1/2 particles. Right? If I replace part of the space-time with some CFT, which has some operator of dimension 1, I can use it to replace this psi -1 here. And so I will just have as one spinor index, essentially. So usually I'm just giving you the spectrum for the flat 10-dimensional space-time. As long as if you pick, so in the bosonic string, you just needed to take some CFT of central charge D to replace some D directions in space-time to get another reasonable perturbative expansion. In superstring, you need to look at theories for which you can define both T and G. So they're called superconformal theories. There are plenty. So and you need to have a theory for which you can do the GSO projection. That's another constraint, which is a little bit less easy to formulate, but it can be formulated. So you need theories that have a very specific anomaly for the action of -1 to the F, which can combine with the anomaly of the remaining fermions and the ghosts. Cancel, modulo 8. So there is a collection of superconformal field theories with central charge D and anomaly D modulo 8. You can just take any of these conformal field theories, combine it with 10 minus D bosons and fermions, ghosts, run the machinery, you get a perturbative background for superstring theory, which might very well not have target space supersymmetry, for example. Because it might be that the setup completely kills the gravitinos. It could be. Or if the superconformal field theory is nice enough, you can preserve some of the gravitinos. For example, the things that are called Calabi-Yau compactifications of superstring theory are situations where you take some nice superconformal field theories of central charge equal to 9. Actually, I was supposed to say 3/2 D, so 9. And you combine it with four bosons and 4 fermions to get 4-dimensional perturbative vacuum of string theory. This conformal field theory of central charge 9 could be geometric, could be a sigma model into some nice manifold called Calabian manifold, or not. It could be not geometric. But anyway, this will give you some examples of, and those preserve supersymmetry in 4 dimensions, some amount of supersymmetry.